So I know I said 4:15, but I got I got stuck in a group for a little bit. So I want actually the group that I got stuck in, which I believe was group 1. I want you guys to share your screen, share your work with the class, and I want you to explain. Before you do that though, but this is what I want you to explain. I want you to explain that last question and see if anybody has any answers. I mean, any questions, because that is, I'm guaranteeing you that's what everyone, the same questions that you had, I guarantee you everyone had the same thing, had the same issues. So before you do that though, so get prepared for that. Before you do that, I would like to ask, I want to share my screen and I want to ask the class just a general question, right? So let's go here. Let's go to my little periodic table. Where's the periodic table? Here we go. Okay, so anybody can answer, yes? So you guys see where iodine is?
Yep, 53.
Yeah, number 53, right? So I don't know how many isotopes iodine has, whatever. But let's say it has isotopes, right? Let's say it's got a couple isotopes. I don't know, it doesn't matter. So that means that this mass that I see on the periodic table, this 126.9, is what?
The average of all of them.
The average of all of the naturally occurring isotopes, right? So naturally occurring, I know we don't talk about that a lot, but it doesn't include radioactive things or things that are unstable, right? So there, because that does exist, but it's only naturally stable isotopes. Okay, great. So that's at 126.9. Okay, can somebody else tell me, if I was to pick up a sample of iodine from, iodine actually is a liquid, but if I was to pick up a sample of iodine and I was to test it, how many atoms of iodine would weigh 126.9?
None of them?
None of them. I don't understand, but that's what the weight is. It says it on the periodic table.
It's the average of all of the isotopes compared to just one.
Oh, I get you. I get you. I get you. Just like the marbles, right? 6.5. None of them weigh 6.5. Okay, so does everyone understand that? Does
Yes.
everyone understand that? Because that's very, very, very important that you get that concept. Yes, that is the weight that you see on there. But if I was to look for an iodine atom somewhere, I'm never going to find an iodine atom, assuming iodine, which it does, but I just don't know the different isotopes. But anyway, if I go and I search for an iodine atom, I'm never going to find an iodine atom that weighs 126.9. And I hope you get that. You understand that. You're never going to find one because that's the average of all of the naturally occurring isotopes. Okay, so that's very important. That's like one of the main concepts of this portal. Another hidden concept is actually that towards the last questions, which is, I want someone from group 1 to share their screen. And let me stop sharing. Share your screen and explain to us, because I know you probably didn't get to finish it, but at least I talked about it with you. And all of you said, you go, oh yeah, you understood, wow. So I want one of you guys to explain it to the class, please. Okay, so how about we start with 9? Somebody from group 1, start with 9, because really the question starts from 9, right? And it works you into like the last question. So I guess for number 9, the first 9A, this should have been really easy, right? Because the average atomic mass, that's straight up where?
The average atomic mass is like on the periodic table, first of all, and then also we solved it in 8A as well. So.
And you also solved it in 8A, exactly, because you took the average, the weighted average of all of those different isotopes, exactly. So, and then can you kind of talk about what you did in B?
So from B, basically how we solve this question is, because like the question is basically asking the average mass of a single chlorine atom, and we took the average atomic mass that we got from 9A and we converted it to grams. And the conversion for that is 1 AMU is equal to 1.661 times 10 to the negative 24th. And that's how we got 5.888 times 10
Where
to the
did you get that conversion? Just out of curiosity.
It was in the video. Oh, it's probably also at the top, maybe. Yeah.
Yeah, there you go. Reading is fundamental. All right, so you got it from there, and basically all you did is a quick little dimensional analysis, and then you got that 5.888 number. Can you explain to the class or ask the class, like, what does that number mean? What does that number tell you? What is that? What is that? It's a bunch of numbers. What does that mean?
So like looking at it, it's 5.888 times 10 to the negative 23rd. And if you think about that, that's a really, really, really small number. And so like thinking about it, what would be that small? That would be like an atom. So that's, it would be like one single chlorine atom.
And if you guys remember, that's absolutely right. So if you guys remember the quick tutorial, I kept giving an example at the beginning. I kept giving the example of if I have one singular atom, and I know how much that one singular atom weighs, and then I did something to that, I would get something else. And that's what we're going to talk about right now in 10. But that's what the weight of one singular chlorine atom weighs. And you can see that. Look how small that freaking is, right? It's like 10 to the negative 23. And all the atoms weigh more or less are on 10 to the negative 23. Different, numbers in the front, but 10 to the negative 23. They're tiny, super, super tiny, which is number 10 is really a really important question because it does two things. It kind of ties in this whole how are these AMUs related to the periodic table, and then it also introduces the mole without really saying anything about the mole because that's what we're going to do tomorrow. But it introduces the mole because that number right there, that 6.022 times 10 to the 23rd, they don't say it's the mole, but that is Avogadro's number. That is the mole, which is super integrated into the periodic table. So can you kind of explain what 10 is asking and tell me how you are going to get the answer?
So basically what it's asking is taking like the answer from 9B, which solving it we found was the mass of one chlorine atom, and basically solving for 6.022 times 10 to the 23rd number of chlorine atoms.
So stop right
yeah.
there. Stop right there. So just to remind, because that might be confusing for people, right? If you remember, one of the first questions in the first page said, if you have 1,000 carbon-12 atoms, right? Do you remember how you got that answer? How did you get that answer? That was really easy. All you did is multiply, right? You said, okay, well, if I have 1,000 carbon-12s and each carbon-12 weighs 12, then I'm going to just multiply 1,000 times 12 and get 12,000. That was easy. This question is the exact same concept. If I have one singular atom of carbon and it weighs that much, but I want to know how much would it weigh if I had that many atoms? If I had 6.022 times 10 to the 23rd, so a crap load of chlorine atoms, right? How much would that weigh if I had that many atoms? So that's all she's doing. All she's doing is taking that many atoms and multiplying it times what each one weighs. And before you put that answer down, Amara, can anybody tell me, anybody other than group one, tell me what you think that answer will be without doing the calculation? Don't do it. Because that's the whole concept here, is that you don't need to be doing calculations. You should be able to reason what that answer should be.
Well, the exponent for the power of 10 is 23, and also if you look at 9b, the exponent is negative 23. So just by laws of exponents, you'll be left with 10 to the 0, which is 1. and then you'll do the other mass, so it'll end up in grams.
Okay.
Well, it's already in grams.
But okay, and that's absolutely correct. But what I want to know is the actual answer without doing the calculation, because the concept behind it is what you need to understand. You're absolutely right. The math, and once you do the math, you'll get it. But I don't want you to do the math. So please, nobody put it on your calculator or your phone, right? So it's you have the weight of one chlorine atom, and you're multiplying it times Avogadro's number. What answer should you get for chlorine? This is for chlorine.
You should okay, I'm unmuted. You should get the average atomic mass.
So what is the average atomic mass of chlorine? It's on the screen, bro.
Is
12.
it's on screen.
It's
12.
30, it's not 12. Chlorine, not carbon.
Sorry.
35.45. That right there should really, that should bring everything together for those of you that are confused, because this is the first time that these POGOs have introduced the mole. And we're going to be using it from now on all the time, every day. But you have to understand that why the mole is so important is because if you take the mass of one atom, whichever atom, it could be hydrogen, helium, carbon, selenium, whoever, it doesn't matter. If you know the weight of one and you multiply it times Avogadro's number, you're going to get the average atomic mass of that thing, of that atom on the periodic table, which is why the mole is so important. Okay, so that's what I wanted to get. I wanted you guys to be able to answer that before you actually did the calculation, because if you can do it and you can reason, then you understand the concept behind this POGO. Okay, do you guys have, and thank you, Amara, that was beautiful. Do you guys have any questions? So it's 4:30. I do want to, no questions. That's amazing to me, but okay.
I actually do have one question regarding submitting the POGO.
Yeah, go ahead.
So another person in our group was actually pulled up the POGO on our browser, and I noticed that when I pulled it up, it was still blank. So is it just one of us in the group that submits it, or do we all submit it with the same answers?
No, it's only one.
Okay, I just want to make sure, because
Yeah,
since
just
we
like
all
you.
didn't get a chance to finish it, I just want to make sure that we could still
No,
upload it.
you work on it together. That's why you have participation points at the end of the week. But you only submit it once and it goes on the Microsoft Teams, just like before.
Okay.
Okay. So tomorrow we're going to start the mole, and we're going to talk about the mole for a couple days, probably tomorrow and Monday, maybe even Wednesday. It's huge, which means that you have to watch the mole quick tutorial before class tomorrow. The quick tutorial is a little bit longer than the usual ones. I think it's like 13 minutes, 14 minutes long. And it's because it's such a big deal. I have a lot to say about it. So you please watch that before class. Remember, we have a study session today at 7. I might be a little late. I might, maybe not. But if I am, don't leave. I'll be there. I have a meeting right before, so I might run a little over. So don't leave. Okay, I will be there. Do you have any questions? Nobody has any questions. Fantabulous. Great. Okay, guys. Well, have a wonderful day. I guess I'll see you later.
Dr. Tony, I still have to.
Yeah, I know.
Okay.
All right. Bye, guys.
Thank
See
you.
ya.
Have a good day.
Welcome. You too.
Bye.
Bye.